as we are discussing the applications of the Biot-Savart's law, and we had already discussed the application of Biot-Savart's law for a straight current carrying wire. Now we are going to discuss the magnetic field produced due to a circular loop carrying current. So there are 3 points over there. We'll find out the magnetic field due to circular loop carrying current. One is at any point on the axial line. Next is at any point on equatorial line. And another one is at the center of the loop. So for that, let us consider a circular loop carrying current, and we are considering two current elements above and below along the diameter of this circular loop. So these red arc represents the current element, and this represents the diameter, and where A is the radius of this circular loop. Let us imagine that current I is flowing through this circular loop in anti-clockwise direction. Now consider a point P in the periphery of this current carrying loop, and this point P is at a distance x on the axial line from the center of this circular loop carrying current. Now let us join these current element with this point, and represents the position vector is r, making an angle theta, because we are just drawing a tangent from this element to the point P. So there is a 90-degree angle between this position vector and the axial line of this circular loop, and dB represents the small amount of magnetic field produced by this current at point P. Let us imagine that as this magnetic field is oblique and a vector quantity, so we are considering that this magnetic field is resolved in two rectangular components, that is dB sine theta and dB cos theta, as this field is making an angle phi with the perpendicular. So for any two diametrical opposite element of the loop, the component of this magnetic field or the perpendicular component to the axis will be equal and opposite, and will it cancel out. So we are again considering that this point is again being joined to the other current element. Again this dB represents the direction of magnetic field downward. Again it is oblique, and we are again resolving this in two rectangular components here. Now what we are observing here, that dB cos phi above and dB cos phi below this axial line are equal and opposite, so they will cancel out, and the axial component will be in same direction, that is dB sine phi for above and below. So they will be get added up in order to find out the total magnetic field. So the plane of coil is considered perpendicular to the plane of this figure, such that the direction of field can be visualized in the plane of this figure. Now applying the Sievert's law. The total magnetic field at point PB, that dB is equals to mu naught I dl sine theta upon 4 pi r square. This is how we are applying the Biot-Sievert's law for this current element dl of this circular loop, as mu naught and I are constant, or we can write it in the form of mu naught I dl 4 pi r square. Now the angle between this current element and this position vector r is 90 degree, because the radius of loop is very small, and we know that sine 90 is nothing but is equals to 1. So the semi-vertical angle made by this vector r to the loop phi and angle between this r and dB are 90 degree. So the angle between this magnetic field is also phi, as we had discussed and drawn in that diagram. So what we are going to have, that we are resolving this as we had discussed in two components. dB cos phi cancel out, and we are considering the effect of this dB sin phi only here. Now the total field comes out to be B is equals to integration of the small magnetic field dB sin phi is equals to mu naught I dl sin phi upon 4 pi r square, and here what we are having, that mu naught I a sin phi, these are all constant, so we can replace these with a single quantity, and we can write here it as B is equals to mu naught I a square upon 2 a square plus x square raised to power 3 by 2, and where these terms are the constant terms. Now we are going to discuss the special cases for this circular current loop. First case is at the center of current loop. We know that this x will be 0, and what we are going to have, that B is equals to mu naught I upon 2a. If the observation point is very far from the coil, in that case a will be very less than this x, and we are having this, the total magnetic field will be mu naught I upon 2a, or a is as replaced by this x, so we are having the net field as B is equals to mu naught I a square upon 2x square. Now we are having that circular coil is there. Now at every point that is being observed, we are having different directions of current at every point for that circular loop. So let us figure out the direction of magnetic field for that corresponding direction of current at every point. So before that, we are going to discuss that for a circular loop, as the distance is being increased, this type of graph we are going to observe that the magnetic field gradually decreases. Now we are having again a plane which is having the circular loop, and the direction of current through this is anti-clockwise. Now we are going to find out the direction of magnetic field for different positions. Now for the point A, we are observing that as the current is entering or leaving this plane, we are having the magnetic field lines clockwise and anti-clockwise. And we are observing that as we are going away from this current carrying point, the magnetic field lines are going far from each other, going apart from each other. So this is one view. In another view, let us consider that this is our circular loop and the current I is flowing like again anti-clockwise. And what we are going to observe, the direction of magnetic field lines at different point. Now above and below you can see that the circular concentric loops are there and they are representing the clockwise and anti-clockwise direction of magnetic field, and at the center the magnetic field lines are going straight, and as we are moving towards these current elements, that is towards the wire, there is deflection in magnetic field lines. Now if we are considering that we are having the circular loop and we are going to find out the magnetic field at the center of the loop. So here the plane which was earlier perpendicular is now lying on the same plane of the figure. So this circular loop is having radius A, current I is flowing, and we are considering an area element, that is the current element dl here, making an angle 90 degree with this vector, that is the radius, and we are going to find out the magnetic field which is entering at the center of this circular loop. And as we had discussed, the plane of coil is now lying on the plane of this figure along this coil. So the direction of current is clockwise such that the magnetic field is perpendicular into the plane, that is the field lines are entering the plane here. So applying the Biot-Savart's law, dB is equals to mu naught ideal sine theta upon 4 pi a square, or as the theta is 90 degree, so the field line or the magnetic field is mu naught ideal 4 pi a square. In order to find out the total magnetic field, we need to integrate this. Now, as the angle between the current element and the radius is 90 degree, so as we had considered, this sine 90 is 1. So the total magnetic field comes out to be mu naught ideal 4 pi a square, and this is equals to mu naught I upon 2a for the whole loop we are going to discuss. Now here again these terms mu naught I, a are constant, and here this integration of this current element is 2 pi a. Now let us discuss the effect of this magnetic field, or when we are going away from this circular loop again, in that case what is the effect on the magnetic field. As we are going away far from this center, in that case the magnetic field is being decreased. So at the center the magnetic strength or the field is strongest. As we are going away from this center, the magnetic field gradually decreases. Now after discussing this current carrying loop, let us discuss a solenoid case. Now what is solenoid? You all aware that a solenoid is something in which we are considering n number of circles concentric or looping over the soft iron core. So a solenoid means an insulated copper wire wound closely in the form of a helix. Okay, so we are having a cylindrical copper wire and we are winding this with these wires. Okay, so the soft core is being wounded by the wire in this manner. Now if the current I is flowing through this solenoid, so we can see that from one point the current is being entering, from other point the current is being emerging out, and with the current we are observing that dot represents the direction of current emerging or the magnetic field lines emerging at these points, and the cross represents the direction of field entering at these points, and this red arrow represents the direction of current. Now we are having that, or we can imagine that we are having so many points, and as these points we can find out the direction of the field as well if the current is flowing, as we had discussed in the case of circular loop. So these small circles represents the direction of field at respective point, and the big circle represents the whole direction of magnetic field lines for this solenoid. And as we can observe that at emerging point the direction of field lines are anticlockwise, and for entering point, that is cross, the direction of magnetic field lines are clockwise. At the center the field lines are going straight, but towards the end of the solenoid they are bending towards these current elements or the sources. So there is a tip to find out. We can see that as the field lines are going away, that end represents the north pole, and from where the field lines are being entering, that represents the south pole of this solenoid. And as we know that the current carrying solenoid always behave as a magnet. It is being represented by a magnet through which the current is being flowing. So there is a tip to remember over here, that when we look at any end of the current carrying coil, if the current is in anti-clockwise direction, then that end of the coil behaves like north pole, and if the current is clockwise direction, then the end of the current or the coil behaves as the south pole of the magnet. In the next topic we are going to discuss about the toroids and the current through a solenoid.